Today we study X27Q entropy. The first one, explain the thermodynamic definition of the entropy of an ideal gas consisting of n molecules. The entropy differential of entropy is defined by the heat transfer to the system divided by the temperature. We, we assume that the system keeps in being in a thermodynamic equilibrium at the temperature T. Into the first law of thermodynamics. In thermodynamics, we have dq, so dq can be replaced with temperature multiplied by the infinitesimal change in entropy. So TdS, dq is to be replaced with a TdS. And this is the input energy to the system, and the output energy will be the work done by the gas, and plus the remainder will change. Whether the remainder is a positive or negative, it will change the temperature of the system. And change in temperature is being considered as the CV, the heat, specific heat, the heat capacity constant volume. So CVDT is identical to the delta internal energy. This the W is the work done by the gas. Note that this is the work done by the gas, and infinitesimal change in temperature is related to the change in the internal energy as a CV times the dt. So we recall the ideal gas equation, PV equals NKVT, from which we can express this P over T to be P over T. So move this guy to the left and move this volume to the right. So P over T is NKV over V. We use this to find the differential of entropy S. So we divide this by T and remove this one. Then we find that CV constant and the dt over T and P over T is NKB over V, NKB over V. So we all have logarithms, differentials of logarithms. We recall that NKB is the difference between the heat capacity, constant pressure, subtracted by heat capacity, constant volume. So we have all of these, and these are all differential of logarithms. By the way, we have pulled out. So wait a second. This one has a dt over t, and if I pull this CV out, and this becomes a Cp over Cv and minus 1. We recall that this is exact NKB, and we have a special parameter, the notation for the ratio of these two heat capacity to be gamma. So it becomes this kind of form. As a result, the entropy change in a finite transition from the initial state with the subscript i's, so temperature, volume, pressure. So not all of them are independent, and if we choose these two, then the pressure is completely determined by temperature and volume from the initial state to the final state. If I consider this differential and integrate over a path from the initial state to the final state, what we obtain is just because it is a dx over x is a d log, so we have a differential of log. So differential if I integrate this, what I get is from I to f, we have log x and xf over xi, something like that. So x depends on what parameter appears in the expression. So because it is a temperature, we have a ratio of the final to initial temperature and logarithm. And then gamma minus 1, we still have this. We can move this guy to the left-hand side. Because of the negative sign, log Vf over Vi is to be replaced with log Vi over Vf. So I have replaced, exchanged the numerator and denominator. And then gamma term is Vf over Vi. Temperature divided volume. So from the equation, PV equals NKBT, temperature divided by volume is a pressure divided by NKB. So what we have is this kind of form. The final temperature divided volume is a pressure of final state, and temperature appears here, the pressure in the initial state. And then in here, this gamma can be moved above. So a log x is log x to the a. So I have moved this parameter gamma. Gamma is the ratio of Cp over Cv. And it, it becomes a power of the volume ratio. Finally, over factor Cv is in here. So we can move this guy too. So we have Cv inside gamma is the power of the Vf over Vi, and this is the pressure ratio. Okay, but we recall that it's gamma equals Cp over Cv. Therefore, if I insert this power, multiply these two powers, so what I get is a Cp for the volume ratio and Cv for the pressure ratio. In this manner, we can compute the change in entropy from the initial state to final state analytically. So, ideal gas equation indicates that only two of the thermodynamic variables among PV and T are independent variables. Hence, the entropy relation is not uniquely defined. We could find many other equivalent processes for delta S in the following way. Because of PV equals NKBT, so we can always multiply 1 with PV equals NKBT. So PV over NKBT equals just 1. So because to the alpha, unity to the alpha is also unity. So we can multiply this factor with arbitrary power. So that does not change the final result. Instead, this multiplication simplifies the expression in terms of only two variables. For example, P among PVT, we can express something in terms of PV, in terms of VT, and in terms of PT. So the following expression for the delta S is not different from the previous result that is expressed in terms of pressure and the volume. In here, we have expressed in terms of temperature and volume. So to make this kind of conversion, this is simply conversion factor. When you replace meter per centimeter, what you multiply is just 1, and 1 is 100 centi, because 1 centi is 1/100th. Multiplied by 1, this is 1. Because it is 1, we can always multiply 1 arbitrary with arbitrary power. In a similar manner, we have what we have done with the conversion is that multiplying the conversion factor to find the relation for delta S in terms of temperature and volume. So pressure and volume and temperature and volume. In addition, this gamma, this Cp over Cv, can always be expressed in terms of this number of degrees of freedom. And the monatomic gas has the F, that is number of degrees of freedom, to be 3. And the diatomic gas, diatomic molecule, we have the 3 translational and the 2 non-vanishing moment of inertia. Therefore, we have 5, and the polyatomic molecule has 3 terms for the translational kinetic energy, and another 3 terms, I1, I2, and I3, that represent the momentum of inertia about all 3 Cartesian axes. So, as a result, we can always express the change in entropy of a thermodynamic system from an initial state to another state, as long as we can find a path along which the system is in thermal equilibrium at temperature, a variable temperature with the environment. We can always compute the change in entropy in terms of this pressure, volume, or pressure and temperature and volume. Any two variables among the all thermodynamic variables. That's it for today. Thank you.